before, we're told that we have a 24-inch stick that's going to be cut up and glued together to form the frame of a box, form this box. So you got this long stick that you're going to cut up into different pieces and glue back together to form that. So we want to do this, and it's going to have a square base, so I've got the width equal to width. There's a height here that we don't know. First thing we're supposed to do is show that the volume of this box can be written as 6w squared minus 2w cubed, where w is obviously the width down here. Well, we know that volume of a box is length times width times height, but in our case, since the width and the length are the same, I can go ahead and say that's w squared h. So it's got two variables in it, and I'll use this additional information that I've got a 24-inch stick that I'm using here. I'll use that information to get a relationship between the h and the w, because you can see that I've got each of these pieces have to be made out of the stick. So I've got to have a w, another w, another w, another w, and up here there's 4 more w's. So I can see that that 24-inch stick is going to be broken up, cut up into 8 pieces, 4 on the bottom and 4 on the top, that have length w, and then the h's, well, I've got 4 of those, so plus 4 h's. So cut that stick up in this many lengths and this many lengths, and then you'll glue them together. Well, that allows me to solve for h in terms of w. So I'll have 4h equal 24 minus 8w. Divide through by 4, and I get h equals 6 minus 2w. I'll take that and put it right there. So now v is only going to involve w, and it's going to be w squared times 6 minus 2w, which is 6w squared minus 2w cubed, which is what we're supposed to show. Now I'll use that, and we've got its derivatives here. I'm going to use that to find the dimensions of the box that will maximize volume. Well, we've already got the formula for volume, and so if I want to maximize volume, I just go through the process using calculus. So I need the critical points, because that's places where I could have a maximum volume. So the critical points are where v prime is 0, v prime does not exist. Well, this doesn't apply. V prime is 0. I guess I need to solve 12w minus 6w squared equals 0. I'll factor out a 6w. Leaves me with 2 minus w. And so I can see w equals 0 is a critical point, but it doesn't make any sense in this problem, because you don't want a width of your box up here to be 0. So I'm just going to use w equal 2 as my only critical point. And I can test that point. I believe that's, yeah. I'm going to test that point by plugging it into the second derivative, using the second derivative test. Or you could set up a sign chart using this factored form. Either one will work. But all I need to know is what happens when the second derivative is evaluated at 2. I get 12 minus 12 times 2. That's going to be negative. And negative means concave down, because that's what second derivative gives me, is concavity. I'm at the top of that concavity, so this is some sort of maximum, which is what we were hoping to show. So that's the width, and oops, go back here. It says I need to determine the dimensions. Well, so now we'll come back and get the, we know the width and the length are the same, so the width and the length are both 2, and then the height's going to be 6 minus 2 times 2. Well, that's 6 minus 4. Turns out it's also 2. So the box that you can create would actually be a cube, all sides equal, if you want to maximize the volume. Last problem, provide a single function that has these properties. It has a local maximum at x equal 1, but f prime at 1 does not exist. It has a local minimum at x equal 2, and a critical point at x equal 3 that is neither a local max or a local min. Okay, so let's start drawing that. So I've got something happening at 1, 2, and 3. So here's 1, 2, 3. It's got to have a local maximum at x equal 1, but f prime doesn't exist. We know that means it's got to have either a cusp or a corner point or something, so I'll just make it a cusp, because that's usually how it occurs for us. has a local minimum at x equal 2. Doesn't say that the derivative has to exist there, but we'll just go ahead and make it a minimum at 2. Whoops, I didn't do very well there. Let me try that again. So I want it to come at 2 is where I need to have a minimum. So something like that. Got a minimum here. And then it has a critical point at 3 that is neither a local max or a min. So we know what that means is that it's going to either have to flatten out, be a slope of 0, or it could also become infinite for just an instant, have a slope of infinite slope or undefined slope. And we'll just make it the easier one, which is, to me, it's have it flatten out and continue on. So it's got a horizontal slope at 3. Oops, and then it goes like that. So there would be a sketch of a graph that has these 3 properties.